All right, here in 6.3, we're going to do kind of the same type of thing that we did in 6.2, where we're going to find the volume of a solid of revolution. And just like in 6.2, the way we're going to describe those solids of revolution is we're going to have some bounded region. So in this case, it's the region bounded by this curve and the x-axis here, shaded in green, revolved around some axis, in this case, the y-axis. And in 6.2, what we learned is how we could figure out that volume using washers or disks. In 6.3, we're going to figure out the exact same volume. In fact, we'll even get the same answers, but we'll use a different method, the method of cylindrical shells. So the idea here, this example is supposed to kind of motivate it. If you were asked to find the volume of the solid that's created by rotating this region around the y-axis, maybe you could see how washers wouldn't work. Because we're rotating around the y-axis, because we're rotating around a vertical line, our variable of integration would be y. So the way you think about it is you take a horizontal cross section here and you try to picture kind of the washer. And maybe you're like, yeah, that wouldn't be too bad. The inner radius would be from my axis here to this point, and my outer radius would be the axis here to this point. Right, but that's problematic. The issue is both this point and this point are determined by this same curve. So it would be really challenging if I had a given y value to figure out what the inner radius is and what the outer radius is, because they both come from this same equation right here. But fortunately, there's a different method you can use. Instead of thinking about this as infinitely many washers, you can think about it as infinitely many cylindrical shells. And so you're like, okay, what's a cylindrical shell? Well, like I did before, maybe I can start you out with some animations to kind of help you wrap your head around what's going on. So here's a region much like the region we had bounded, and here is a very slow animation of revolving that region around the y-axis and sort of the resulting solid that you get. It's meant to be the same picture that I drew. This is just done a lot better because I can't draw. So this is the thing we're trying to find the volume of. You can kind of picture a bundt cake. I think that's a word or a thing. That's how books always describe solids like this. So how are you going to find the volume of that solid? Well, here's an animation that kind of shows you. The key thing to know, though, is that these partitions, they should be infinitely thin. We're giving them some thickness here to try to make this make sense, but when we actually figure this out with calculus, they'll each be infinitely thin. But the idea is each of these are kind of half of a cylindrical shell. So pictured in light blue, for example, maybe you can see half of a shell. If this went all the way around, if it went around the front as well, then what you would have is what's called a cylindrical shell. And maybe you can kind of see how if we added up the volume of each of these different colors, how that would approximate the volume of the entire thing. It might be easier to see if you don't just have half cylindrical shells. So here's where you have the entire cylindrical shell. However, since they're solid, it makes it a little bit hard to see what's going on. But all we're going to do is we're going to figure out the volume of each layer individually, and then we're going to add up all those different layers using integrals. Switching over to your textbook, here's some more images of cylindrical shells. This is a different curve, a different bounded region that we're revolving around the y-axis, so we get a different three-dimensional solid here. But with this solid, we can also build this out of cylindrical shells, and here's kind of the idea. If each of the shells have thickness, it kind of looks like it does in this picture, but if we make the shells thinner and thinner, or infinitely thin when we finally integrate this thing, all the shells together kind of make up the solid that we're looking at. A few years ago when I was teaching this, a student told me to think Russian nesting dolls. If that helps you at all, that's great. Another way you can think about it is kind of a paper mache idea, if you've ever done that. If you get a piece of paper and you wrap it around something, it doesn't seem like it's getting any thicker, but it does. It gets a little bit thicker. And if you put more and more and more and more paper around the outside of something, it gradually increases its thickness. If we could figure out the volume of each of those individual pieces of paper and add them all together, what we'd get is the volume of the entire thing. So maybe that gives you some intuition about what we're doing with cylindrical shells. But the big question is going to be, wait a minute, I had to figure out the volume of the washers earlier, and that was easy enough because washers is just sort of a three-dimensional analog of a circle with the circle missing, and I could figure out the area of the outer circle and subtract the area of the inner circle, and then multiply it by this infinitely thin width, and I'd have the volume of each individual washer. That's all great, except the problem is these cylindrical shells are not washers. I need to figure out the volume of an individual cylindrical shell here. And the infinitely thin part is now its thickness going in this direction. So I need some sort of geometric formula that will tell me the volume of what we have pictured over here, any individual layer of these cylindrical shells. And this picture does a pretty good job at it. The idea is if you have a cylindrical shell, you can kind of cut it somewhere, cut it straight up and down here, and then kind of unwrap it. And if you unwrapped it, it would turn into this big long rectangle, this rectangular prism. And to figure out the volume of this thing, well, all I need to do is figure out the area of kind of the front face, just like I did with the washers, and then multiply it by this infinitely thin thickness. And the good news is the area of a rectangle is about as easy as it gets. All I have to do is multiply the height times the base. The base is kind of the tricky one, but the way to think about it is if we're rotating around the y-axis, then the x value refers to the radius of our cylindrical shell. The base of this rectangle is the same as the distance all the way around the bottom of our cylindrical shell. Well, the distance all the way around the bottom of our cylindrical shell, I can just use the circumference of a circle formula. The circumference of a circle is 2 times pi times r. The distance around the circle that makes up the base of this cylindrical shell is going to be 2 times pi times the radius. And again, when we're in the instance where we're rotating around the y-axis, the radius is just the x value. What I'm saying is the length of the base of these rectangles that we need to figure out the area of is 2 times pi times whatever the x value is, because the x value is the radius when we're revolving around the y-axis. And what about the height? For the height, all I need to know is what is the height of the curve that gave me the bounded region that I rotated around the y-axis to create this solid of revolution. Well, it's easy enough to figure out the height if I know the x value. The height of the function at that x value is just f of x. So our big formula, the big takeaway for cylindrical shells is we're going to be adding up infinitely many of these shells. And we'll talk a little bit about your bounds of integration when I give you a hard example. And the volume of each shell is just the area of the front of the shell times the thickness. The thickness will be the dx part. It's going to be infinitely thin. And to get the area of the front of this rectangle, all I got to do is take 2 times pi times the radius, which x will represent, times the height, which f of x will represent. So if you thought of the 6.2 formula as kind of being we're going to integrate from somewhere to somewhere, either with respect to x or with respect to y, depending on whether we're revolving around a horizontal line or a vertical line. And then what we integrated was kind of pi r squared minus pi r squared, where capital R represented the outer radius and little r represented the inner radius. And both of those we kind of determined based on the function that we were given. I put formula in quotes because I don't know if that's really a formula, because there's a lot of things you sort of have to figure out to use this. But that's sort of the idea of the formula from 6.2. The idea of the formula from 6.3 is we're again going to be integrating. And if x is our variable of integration, in the next example we'll see how it could be y. But if x is your variable of integration, then it's just 2 times pi times x times f of x. You're like, whoa, that's a lot to remember. Yeah, but it's not that bad if you have memorized that 2 pi r is the circumference of a circle, and then this is the height of your cylindrical shell, and this picture makes sense to you. Like, yeah, to figure out the area of this thing, I would cut this guy, and so the length of the base here would be the same as the distance around this circle down at the bottom here. That's all pretty abstract. Maybe I can use that knowledge to solve this question, and then we can call this good. The first comment I want to make when trying to solve this thing is what is infinitely thin here is the thickness of our shells. If one of our shells goes right here, the next one's just barely outside of it and just barely outside of it. Think this picture, except the width of each of these different bars is infinitely thin. The infinitely thin thing is the x value here. When I rotate around the y-axis, the x value is my variable of integration. What I'm saying is that if you're using the method of cylindrical shells and you rotate around any vertical line, so for example, the y-axis like we did in this example, then our variable of integration will be x. We'll have a dx at the end of our integral. And similarly, if you rotate around a horizontal line, so for example, the x-axis, then your variable of integration will be a y. And I just want to make the point that that's the exact opposite of what happened with discs and washers. With discs and washers, it was horizontal lines that we rotated around where our variable of integration was x. And it was vertical lines that we rotated around where our variable of integration is y. And if you want, you could just memorize all this stuff like a chart. But if you can sort of understand why this all makes sense, that's ideal. With cylindrical shells, when we're rotating around a vertical line, then our different shells are infinitely thin in the x direction. Whereas with discs and washers, when we rotate around a vertical line, then our washers, which would lay flat this way, would be infinitely thin in the y direction. It's also worth pointing out that with discs and washers, we rotated around vertical lines other than just the y-axis. Like we rotated around the line x equals 2 or something. With cylindrical shells, you can do that. It still works out, but we're never going to bother in this class. In this class, I'm going to pick my battles, and for cylindrical shells, we're always going to either rotate around the x-axis or the y-axis, which is why I include that parenthetically in this little chart. Why don't we solve this problem? So what we're going to do to figure out the volume of this guy is we're going to add up infinitely many cylindrical shells. So it might help just to picture one of them. So I'm just going to arbitrarily pick any x value I want. It doesn't matter which one. Maybe this x value right here. And I'm going to think about what that shell would look like. Here it is as best as I can draw it. This thing is completely hollow. There's no top on it or anything like that. Think it's a piece of paper if you sort of rolled up a piece of paper. It's a piece of paper going on the outside. And the radius of this cylindrical shell is just the distance from my y-axis here to this point. So it's whatever that arbitrary x value was that I chose. And the height of this cylindrical shell is just the height of this green curve at that x value. So I can just refer to it as f of x. And conveniently enough, that's given to me down here. So I want to integrate, and I'm going to integrate with respect to x because it's in the x direction that these guys are infinitely thin. And I'm going to think about, okay, what do my x's go to and from? Well, the smallest my x is ever going to be is right here where my x value equals 0. And the largest my x value is ever going to be is at this point right here. I think this ends up being at 4 because if my x value equals 4, 4 minus 2 is 2, and 2 squared is 4, and the negative of 4 is negative 4, plus 4 more gets me back down to 0. So when I put either 0 or 4 into this equation, it looks like 0 comes out. So when the x value is either 0 or 4, the height of this green curve equals 0. So you can get those bounds of integration just kind of by arguing your way through it like I did there. But maybe what would be easier in this case is this region was really bounded by the curve y equals negative x minus 2 squared plus 4 and the x-axis. And the x-axis comes from the equation y equals 0. So what you could do is take these two guys and set them equal to each other and solve that equation. And I think you'll get for your solutions 0 and 4. Don't worry, we'll see more examples of that in future videos. Okay, so what do I want to integrate? It's always going to be 2 times pi times the radius. And the radius is going to be my variable x here, the distance from here to here, times the height of that cylindrical shell, which is f of x, which is given to me by this equation right here. Integrate this thing and you're done. That's it. Much like in the previous section, the hardest part is just the setup. Figuring out that this integral corresponds with the volume of this shape, that part's hard. Figuring out the value of this integral, that's not bad at all. We'll do that below in just a minute. But really, I think at least 3/4 of the work is just getting this far, just understanding where this comes from. I almost want to just quit this here and not even integrate this thing to really emphasize how all the work comes getting to this step and not beyond it. But just for the sake of completeness, I guess I'll finish. The 2 and the pi are both constants, so I can pull those out in front of the integral. And then maybe I'll expand this x minus 2 also so I can work on getting rid of some parentheses. That gets me this far. And now I can take this negative and distribute it through the parentheses to get rid of this set of parentheses. And when I change the sign on each of these 3 terms to get rid of these parentheses, a nice thing happens. I got a negative 4 and a positive 4. So those guys will just cancel each other out. And now I can take this x and distribute it through the parentheses again to get rid of this next set of parentheses. And I'm left with just this to integrate. And I think this will be easy enough to integrate because I just got to use the power rule. The antiderivative of negative x cubed is negative 1/4 x to the 4th. And the antiderivative of 4x squared is 4/3 x cubed. And I'll need to evaluate that from 0 to 4. So let's see, changing all the x's to 4s, 4 to the 4th power. Well, one of those 4s will cancel out with this 4 here. So really I'll get 4 to the 3rd power, which is 64. And it's negative because of this negative. And then over here, 4 to the 3rd power, 64 times this 4 gives me 256 over 3. And I guess if you wanted to, you could show that when you evaluate this at 0, you just get zeros. You really don't even need to write that. Getting a common denominator, 64 times 3 is 192. And negative 192 plus 256 is what, 64? So I get for my final answer 128 pi divided by 3. But whatever, that's just plugging in a whole bunch of numbers and knowing 2 fairly easy antiderivatives. The vast majority of the work is getting to this step right here, which is what I want to focus on in this video.